Okay, let's get into this. You know how there are just some ideas, right, that our human brains, they just fundamentally struggle to really wrap themselves around?
Oh, absolutely.
Yeah.
Yeah, concepts that just, they defy our everyday intuition, like trying to really imagine something that's always existed,
Yeah.
not just a really long time,
Mm.
but literally no beginning, ever.
Right, like that pool analogy from the sorts, you've always been in the water, you never got in, or like a road that just goes on forever in both directions, no start, no end.
Mhm.
Our minds just crave those boundaries.
Exactly. And then the flip side is trying to picture actual nothing. You try it and you probably think, well, darkness.
Hmm.
But darkness isn't nothing. It's the absence of light. Okay, so empty space. But, empty space is still something, it feels like our perception needs, well, something to hold on to.
It's like our everyday experience just puts us in this box. But here's the really cool part, and what the source gets at.
Mm.
Even if we can't feel or picture infinity or nothingness,
Uh-huh.
we can describe them perfectly with math.
Precisely. Mathematics gives us the tools, the language. We have the number 0 for nothingness, symbols for infinity, concepts in set theory like the empty set.
It all works out mathematically.
Yeah, the logic holds up. It's rigorous, even when our gut feeling is just like lost. So math lets us explore these places beyond what we can sense.
Which naturally leads us to the next big mind bender from the source material. Dimensions higher than the three we know and love.
Right. Same problem again, isn't it? Just like infinity or nothing, trying to intuitively grasp a fourth dimension or a fifth or, well, an eighth. It's really tough for our 3D wired thinking.
We get the simple progression, though. You start with a 2D square, right?
Right.
Length with x and y axes, easy. Add a third axis z for depth or height. And you get a 3D cube. We see those all the time. It feels totally normal.
And the math follows neatly. You just add another coordinate. So
Yeah.
theoretically, you just add a fourth axis to that 3D cube.
Yeah.
The math describes a 4D cube, a tesseract, no problem.
But picturing it, my brain just goes, nope.
Yeah, you can't really see it or perceive it directly with our senses. But just like 0 or infinity, the math handles it. We can represent it mathematically, draw projections of it in 2D or 3D.
Like shadows, basically.
Exactly, just shadows of the real thing. They give you a hint, but it's not the object itself.
And in theory, you can just keep going. Adding axes for 5D, 6D, 100D, it just doesn't stop.
Mathematically?
Nope.
No limit. The math provides the framework to talk about and work with these higher dimensional spaces, even if we can't, take a vacation there.
And that is where things get incredibly interesting and brings us right to the heart of our deep dive today. Our goal here is to really explore this whole idea of higher dimensions, zooming in on this amazing 8-dimensional structure.
E8.
E8, yeah. And look at how some scientists think it might actually be the key to understanding the fundamental nature of the reality we do see.
And we're drawing heavily from a YouTube video transcript, Hacking Reality,
Yeah.
which really lays out this geometric angle on physics in a fascinating way.
Okay, so let's dive into this abstract 8-dimensional space. What exactly is this E8 structure the source talks about?
So it's called E8. And you should think of it less like, a simple shape like a cube,
Yeah.
and more like an incredibly intricate, highly symmetrical structure, almost like a crystal, but existing in 8 dimensions.
E8 sounds important, almost like a code name.
Well, mathematically, it is incredibly fundamental, and where it comes from, as the source explains, is actually tied to something we can kind of visualize, at least in lower dimensions. Stacking spheres as densely as possible.
Oh, like trying to fit the most oranges into a crate.
It's exactly that idea. Let's start simple. In 2D, how do you pack circles on a flat surface so they take up the least space? It turns out to be that hexagonal pattern like a honeycomb.
Okay, yeah, I can picture that.
Now imagine you put a dot right in the center of every single circle. Then you erase the circles themselves. What you're left with is a specific pattern of dots, a point space that represents that densest 2D packing.
Got it. A grid of points based on the circle centers.
Now, jump to 3D. Stacking spheres, like those oranges. The way you see them stacked in a pyramid shape at the grocery store, that's the densest way. And the source points out something amazing, proving that this specific way is the absolute densest packing possible in 3D. That was a huge mathematical challenge. It wasn't fully proven until 2014.
Seriously, that seems so basic, almost obvious.
It shows how complex these things can get. But apply the same logic. Put a point at the center of every sphere in that densest 3D stack, take away the spheres, and you've got the point space for the densest 3D packing.
Okay, so E8 is just doing that same thing, but scaling it up to 8 dimensions.
Exactly. E8 is the point space, the specific lattice or crystal structure you get that represents the unique, most efficient way to pack identical spheres in 8-dimensional space.
Right. So we have this mathematically perfect, very abstract structure sitting in 8 dimensions. How does that connect to, like, the real world, to electrons, photons, gravity, the stuff around us?
Okay, so this leads us straight into one of the biggest quests in physics, trying to unify Einstein's theory of general relativity.
Which describes gravity and big stuff, like planets and galaxies, as space-time curving.
Right, geometrically. Unifying that with quantum mechanics, which is our super successful theory for the tiny stuff particles, forces at the smallest scales. Finding one single theory that covers both. That's the search for a theory of everything, or quantum gravity.
The ultimate physics challenge, basically, bringing the big and small together.
Exactly, and for a long, long time, one of the main players, the big hope, was string theory. As the source talks about, it got huge attention, tons of funding, dominated theoretical physics for years.
But the source we're looking at, drawing from physicist Garrett Lisi, has some, let's say, pointed critiques of string theory.
It does. The argument laid out is that, well, despite all the work and the hype, string theory hasn't really delivered on making successful, testable predictions. It also, apparently, made some big assumptions that weren't necessarily justified, maybe overpromised, and got incredibly complicated mathematically.
And it suggests it kind of stuck around partly due to academic inertia.
Yeah, established professors, funding streams, PhD programs. It built up momentum that was hard to shift, even with these issues.
Okay, so if string theory maybe wasn't the golden ticket, where else could physicists look? Back to geometry.
That's the angle this source explores. Remember, Einstein showed gravity is geometry's space-time curvature. So the question became, what if the other fundamental forces, and maybe even the particles themselves, could also be described geometrically?
Describing a particle geometrically, that sounds weird. How would that even work?
Well, the source explains this concept that's actually been around in physics for a very long time, like decades. The idea of mathematical fibers attached to space-time.
Fibers, like
Yeah.
little threads sticking off reality.
Sort of, but mathematically speaking. The source gives a helpful analogy. Imagine you live in a totally flat 2D universe, like a sheet of paper. A particle in your world, maybe a photon, isn't just a dot on the paper. It's also represented by, say, a point on a little circle that's attached to that dot on the paper. But the circle itself exists in a higher dimension, maybe the third dimension, poking up out of your flat paper world.
Okay, so the 2D particle is linked to something happening just outside its reality.
Exactly. That little circle, that fiber, represents some internal property or freedom the particle has, but it plays out in that extra dimension. And here's the crucial part. Different particles and forces are represented by different kinds or combinations of these higher dimensional fibers. These combinations are described by specific mathematical structures called Lie groups. The source mentions, for instance, the weak nuclear force involves a Lie group that mathematically describes like 3 circles twisting around each other in a specific way.
Okay, so if we scale that analogy up from 2D plus a fiber to our actual 3D universe.
Right. The idea is that at every single point in our 3D space, well, 4D space-time, there are these much more complex, higher dimensional fibers attached. And as these fibers twist and connect and change across space-time, what we perceive down here in our 3D world are particles moving and forces acting.
So just like gravity comes from space-time curvature, the other forces, they come from the twisting or curvature of these geometric fiber things.
That's the geometric picture, precisely.
Yeah.
And the source makes a key point. This whole framework describing forces and particles geometrically using fibers and Lie groups, it's not some brand new fringe idea. It's been mathematically established standard physics for over 70 years. It just kind of got overshadowed by string theory for a while.
Okay, that's fascinating. So this mathematical language was already there. String theory had its run. Now, where does Garrett Lisi's specific work fit into this picture?
Lisi basically took this established geometric language of fibers and Lie groups for particles and forces, and he tried to combine it with Einstein's geometric description of gravity. He asked a huge question. Can we find one single, unified mathematical structure, one big Lie group that contains all the known fundamental particles and forces?
All of them in one structure. And did he find one?
This is the core discovery highlighted in the source. He mathematically combined the Lie groups for everything known as electrons, quarks, neutrinos, photons, the W and Z bosons for the weak force, gluons for the strong force, all of them. And he also included the graviton, the hypothetical particle for gravity.
Okay. And did they all fit together neatly?
Amazingly, yes. They combined perfectly to form one single larger Lie group structure. And that specific structure, it turned out to be E8.
Ooh, Oh, the same E8, the eight-dimensional crystal structure from the sphere packing.
The very same one. E8 is known among mathematicians as arguably the most beautiful, most exceptional structure in all of mathematics. And Lisi found this incredible, unexpected correspondence. The actual particles and forces we observe in nature seem to perfectly map onto the mathematical components of this E8 structure.
That feels like it can't be a coincidence.
That's the feeling.
Yeah.
It's seen as a really potent clue, super encouraging for finding that unified theory. Now, the source is clear. It's not yet a fully proven finished theory. There are still discrepancies, details being worked on, but the sheer fact that the particle zoo we see fits so elegantly into this abstract mathematical object, that's huge.
So if we try to visualize this, even as just a metaphor, the source talks about E8 being like a machine operating behind the scenes.
Yeah, it's a helpful, if simplified picture. Imagine this eight-dimensional E8 structure as fundamental. What we experience as different particles in our 3D reality, an electron behaving one way, a quark another, a photon another, might just depend on what that underlying E8 machine is doing, how it's oriented or vibrating in those hidden dimensions relative to us.
Meaning, they aren't fundamentally different types of things, but different states or views of the same underlying E8 geometry.
That's the profound implication. All particles, all forces, maybe even space-time itself, could just be different geometric aspects of E8, capable of transforming into one another according to its rules, which leads to that really weird thought. Are all fundamental particles basically the same thing underneath?
That is elegant, but yeah, deeply weird. Why would this abstract thing from 8D sphere packing connect so directly to our physical world?
And that loops us back to that fundamental question, maybe the fundamental question. Why is the universe understandable through mathematics at all? Why do these purely abstract structures seem to provide the blueprint for physical reality? The source uses this amazing phrase, asking if maybe we're living in a bit of mathematics that's come to life.
Yeah, that phrase really hits home. Okay, now the source material also brings in another related theory, right? Building on this geometry as code idea.
Yes, it discusses emergence theory, which is being developed by a group called Quantum Gravity Research, with Clay Irwin as a key figure. Their central idea is that reality at rock bottom isn't made of tiny little balls or strings, but is actually a kind of geometric code or language. And crucially, it's deeply connected to E8.
A code written in shapes, like the universe is literally geometric information.
That's the proposal. They even suggest a fundamental pixel of reality at the very smallest scale possible, the Planck scale. And in their model, this basic 3D pixel isn't a point, it's a tetrahedron. You're shaped with four triangular faces, like a little pyramid.
Okay, so space is tiled with tiny tetrahedra.
Not just tiled randomly. They propose these tetrahedra linked together according to very specific rules, forming this incredibly complex dynamic network throughout all of space. They call it a quasi-crystalline spin network. And the rules governing this network, its structure, are derived directly from E8.
Quasi-crystalline. Okay, we heard about crystals, the repeating patterns. What makes something quasi-crystalline?
Good question. The source explains it well. Normal crystals have patterns that repeat perfectly and periodically, like tiles on a floor or a simple cubic grid. Quasi-crystals are different. They have order, definite symmetries, but they never repeat perfectly. The source uses the analogy of projecting a higher dimensional crystal down into a lower dimension.
The shadow idea again.
Exactly. Imagine a perfectly repeating crystal lattice, but in, say, 5 dimensions. If you shine a light through it and project its shadow onto a 2D screen at just the right angle, the 2D shadow pattern will have intricate symmetries, but it won't be periodic. It won't repeat itself exactly. That's a quasi-crystal. And E8 itself, that 8D lattice from sphere packing, is a type of 8-dimensional crystal.
So emergence theory takes the 8D E8 crystal
and projects it down. Specifically, they propose projecting the E8 lattice from 8 dimensions down to 4 dimensions, and then projecting that down into our 3 dimensions. And the key is how they project it at a very specific angle related to the golden ratio, an irrational number. This irrational projection angle is what ensures the resulting 3D structure is quasi-crystalline, not just a simple repeating pattern.
Okay, so projecting E8 in this specific way creates this complex, non-repeating but ordered 3D structure made of tetrahedra.
Precisely. And the claim is that this specific 3D quasi-crystal is a language or code. It consists of a finite set of geometric symbols or letters related to the tetrahedra and how they connect, with strict grammatical rules for how they can combine. But there's enough flexibility within those rules for the patterns to encode information, to essentially write reality.
And the patterns, the meaning, encoded in this 3D geometric structure, That's what we experience as physics.
That's the core idea of emergence theory, yeah. This dynamic 3D quasi-crystal network filling space-time is the code, and its changing patterns are what manifest as particles, forces, energy, and the laws that govern them.
This sounds very different from the string theory picture, where the extra dimensions are supposed to be tiny and curled up, hidden from view.
It's definitely a different approach. In string theory, you need to somehow access those tiny extra dimensions to see the fundamental reality. In emergence theory, you don't necessarily need to go to the eighth dimension. The crucial information and mathematical structure of the eight-dimensional E8 object is supposedly encoded within the dynamics and geometry of the three-dimensional quasi-crystal itself.
So the 3D quasi-crystal pattern contains the essential information from the 8D E8 structure.
That's the argument. Mathematically, they claim, you can work backwards. You can analyze the structure and information present in the lower dimensional quasi-crystal network and recover the fundamental physics described by the E8 lattice.
Man, this is really pushing at the absolute edge of what we think reality might be, this whole search.
It's described in the source as the ultimate treasure hunt, doesn't it? Trying to figure out what the universe is actually made of at the very bottom.
So if these kinds of ideas, maybe Lisi's E8 model, maybe emergence theory, maybe something else along these lines, turn out to be right, what are the implications?
Well, understanding reality at that fundamental geometric, maybe even pixelated level, the source suggests it could open up a treasure trove of new physics, potentially leading to revolutionary technologies we can't even imagine yet. And it might also give us completely new ways to think about the weirdness of quantum mechanics, maybe even consciousness itself.
It really underscores that big breakthroughs often need that kind of radical, outside-the-box thinking, doesn't it?
Absolutely. And the source concludes, whether these specific theories end up being the final story or not, the underlying idea that our reality might be profoundly linked to these beautiful, abstract, higher dimensional mathematical objects like E8, that idea itself is powerful. It remains a really intriguing and kind of mysterious possibility on the road towards a true theory of everything.
Wow. Yeah, we've covered a lot of ground in this deep dive. It's pretty mind-bending stuff. Started with things like infinity and nothingness, concepts our intuition just fails on.
Then navigated into the purely abstract realm of higher dimensions where math becomes our guide.
And discovered this specific, incredible eight-dimensional structure, E8, emerging from something as basic as packing spheres efficiently.
And then explored these theories, suggesting E8 might be the secret blueprint for, everything, all the particles, all the forces, maybe space-time itself, possibly even forming a literal geometric code for reality, like in emergence theory.
The really stunning thing, the core mystery that remains, is just this deep, unexpected link between pure mathematics, especially a structure as unique and exceptional as E8 and the physical universe we actually live in. It feels like.
Yeah.
Like we stumbled upon the universe's operating system, maybe.
It definitely leaves you with a huge question to chew on.
It really does. What if the universe isn't just described by math? What if, at its most fundamental level, it is math? Or geometry? A structure hidden in dimensions we can't access directly, but whose shape dictates everything we see and experience.